Hi all, welcome back to the session of Power Electronics and Instrumentation. We were discussing about the module 1 about the thyristors. Today's session we will discuss about the turn off mechanism. So far we have seen what are the characteristics of a thyristor, how it is going to its on state and how the different layers and the different junctions that are present within the thyristor goes off and goes on, that is forward biased as well as reverse biased, and we have seen the different turn on methods by which we can turn on the thyristors. Along that we have seen the different triggering circuit methods by which we can generate the pulses. Since we know that the thyristor is a turn on controlled device, so we have seen that how we are going to control the on state of a thyristor by varying the firing angle. So in today's session we will discuss about the mechanism that is involved, how we are going to turn off the thyristor. So in turn off mechanism, similar to the diode, you might have studied while studying the diode characteristics that when we are going to turn off the diode, we are going to come across two different concepts, that is the recovery time and the recombination time. So here also in case of a thyristor, we have the four regions, that is a P, N, P, N. So here also similar to that of a diode, during the on state we require this gate terminal to help in the controlling on time of the thyristor. Once the thyristor is in its on state, then it will continue to be in the on state. So we have to turn off the thyristor. During the off period, we cannot achieve any control over the thyristor. Hence, these thyristors are controlled only during turn on. Whereas the diodes, what we had studied, that is in the introduction part, we had discussed about the diodes. We said that the diodes cannot be controlled during on, cannot be controlled during off. Once we have connected the diode in a circuit, it continues to operate on and off depending on whether it is an AC signal or the DC signal. Okay, so that is an uncontrolled device. Whereas we spoke about the transistors, the family of transistors, where if you give, say for example a BJT, if you give a base current to the BJT, then the BJT goes to the on state. If you remove the base current, what happens? The BJT goes off. So BJT or any type of transistor belongs to the controlled on. You are able to control its on period as well as you are able to control when it can be off. So controlled turn on and turn off devices are the family of transistors. Whereas the thyristor family, what we are studying now, is only controlled in its on state by using the gate terminal. Once you have applied the gate trigger voltage here, what happens? These all the junctions, we know that how many junctions are there? 3 junctions, J1, J2 and J3 junctions are broken down and there is a complete flow of anode current. Okay, so this is what we have studied basically in the static anode cathode characteristics of a thyristor. So using the same concept, we are going to study how we are going to turn it off. Okay, so the process of turning off of a thyristor is also termed as commutation. So commutation means it is a process of turning off of a thyristor. That process is known as commutation. So in case of commutation, now it depends on what type of anode to cathode voltage you are applying, whether it is an AC voltage or whether it is a DC voltage. So depending on that, we are going to classify this commutation process. So before classifying the commutation process, now let us understand how this 4-layered device thyristor is going to go to its off state. Okay, the general process how it is going to its off state. Okay. So, we will see the different waveform, and according to the waveform, let us analyze how it is going to its off state. So, now in order to understand the turn off mechanism in a better way, we need to understand the graph. Okay. So, in general, let us consider a diode. We are connecting a diode here, right, and it is connected to some load, let us say an R load. We are going to provide the supply. Okay. So, this is the supply what we are going to apply across this terminal. Okay. If suppose in the case of this circuit we are going to use an AC supply as the input, then what will happen? During the forward, that is, we have continuous cycles like this. We have a positive cycle as well as a negative cycle. So, in the positive half cycle, what happens if we are connecting here? Anode, this is the anode of a diode, this is the cathode of a diode. So, we have the anode and it is connected to the positive half cycle. So, what will happen? It will go to its forward biased condition. We already have understood that forward biased condition means it is the on state. Okay. Similarly, when we come to this part, negative potential is being applied across the diode, what happens? Automatically diode goes to its off state. Okay. This at the instant when it is going to go to 0, when the waveform is going to go to 0, then the diode will not automatically switch on, go to its off state. Why? Because of the presence of minority charge carriers. Okay. It will take some time to settle down and then it will go to its completely off state. Okay. Now, the same concept we are going to use here in the thyristors, which is having a PN junction device. Okay. So, here in this we know that only if there is a anode current flowing in the thyristor, only then the thyristor will be in its on state. We know that. Okay. So, if we want to achieve the off of the thyristor, then what we should do? We have to reduce this anode current equal to 0. We have to reduce the current flowing. Reduce the current flowing means we have to completely make it as 0 current flowing. When will this be a 0 current? When all the junctions are in its reverse biased condition. Okay. Along with this, the anode to cathode forward voltage, what you are applying, it also must be equal to 0. So, only when these two conditions are satisfied, we can say that the thyristor will be in its off state. First condition is anode current should be reduced. Anode current means what? We already have studied the latching and the holding current. So, the latching current whatever we have is the current that is flowing in its on state. Holding current means this holding current is discussed when we are going to its off state. Okay. Now, the anode current must be made less than this latching current. Only if the current is less than the latching current, then we can say that we are reducing the current and we are going to make it as a 0 current. Provided if the latching current is there, is gradually being reduced within the 4 layers, then what will happen is there will be some voltage already present. So, as you are reducing the latching current and again you are applying the potential across this anode and cathode, then what will happen is there are chances of the thyristor getting turned on again, okay, without the help of the gate. So, in order to avoid that false turning on of the thyristor, we have to ensure that the anode current is completely 0. Along with this, the voltage also is reduced or 0. Okay, only if this is satisfied, voltage is also reduced within this layers, then only we are going to achieve the turning off. Commutation is achieved. Okay, so now let us come back to this waveform. Initially, as I said in case of a diode, as soon as the current is going to 0, what happens? Let us say this is the anode current. So, in this case of the anode current here, we have a high anode current, means it is still in its on state. At this instant of time t1, we are going to reduce the anode current to 0, means it is going to go to its off state. What has to be done? We require a steady state on, turn on, and steady state turn off. This is our aim. Steady state means there should not be anywhere. You on the switch, it has to go to on state. You off the switch, it has to be off instantaneously. But what is happening here? Here, as the anode current is going to 0, it has to be completely 0, straight line. But what is happening? There is a reversal of current taking place. This is the anode current. So, there is a reverse current flowing. Why this reverse current is flowing here? This reverse current is flowing because of the minority carriers present here. Okay, coming to the P-N regions of a thyristor. P region, holes are in excess. N region, electrons are in excess. Okay. Now, when we say at the instant, when J1 and J3 are reverse biased, we already go to the off state. Okay. So, what happens? Reverse bias means whatever the combination was present between an electron and a hole, this combination, this bond has been broken, and again the holes and electrons are settled. Okay. But what happens? J2 will be still in the forward bias condition. Already I have explained to you in detail in the static characteristics. Okay. So, J2 will be forward bias. Because of this J2 forward bias, a minority carrier present, what happens? There will be some reverse leakage current. This we have studied in the static VI characteristics of a thyristor. Okay. Using the same concept again, J2 will be in the forward bias condition, whereas J1 and J3 will be in the reverse bias condition when we are going to turn it off. Because of this J2 present, the small leakage current will be flowing in the reverse direction. Reverse direction, why? Because it is a minority current. Okay. So, till where it flows, till some voltage is developed, and what will happen? Once all the electrons and holes have been paired here, now J2 is ready to break. The bonds are ready to break down. And what happens? Whatever the free electrons and holes are there will go and recombine itself. Okay. So, this period from T1 to T2, there is a current flow due to the excess of minority carriers present in the 4 layers, and T2 to T3, what happens is the current will be reduced. It keeps on decreasing, whereas the voltage will be developed here and the current starts reducing. Means it is now going to go to its off state. Electrons will be in motion. Suddenly, if you are going to stop the electrons, it cannot stop because of its mobility. Okay, that is why we are going to have this reverse current. Is it clear? Now what is going to happen? This free electrons that are available, which are constantly moving, slowly it will settle down. So, this total time, that is from T1 to T3, is known as the reverse recombination time. Okay? It is known as reverse recovery time. This TRR is known as the reverse recovery. It is going to be recovered. What is going to be recovered? The free electrons which were in motion, suddenly you are going to apply a negative voltage here. So, it has to come to rest. This process is known as reverse recovery. Once it has been recovered, then the recombination, go back and settle. That is when your J2 is also going to go to the reverse biased condition. Only when all the 3 junctions are in its reverse bias condition, only then the voltage also will reduce, and already current is being reduced here. So, similarly voltage also drops, and hence we can say that the thyristor is completely in its off state. Okay. See here, at the instant T1, the anode current is 0. You have made the anode current 0, but still what happens? Thyristor is not completely off because there is some leakage current present, reverse current. T1 to T3, what is the sequence of operation that is happening? The anode current which you had made it as 0 now flows in the reverse direction because of the excess minority carriers. So, T1 to T3 anode current in reverse direction is flowing. Okay. Now, at the instant of T2, what is going to happen? A reverse voltage is developed. Okay. A reverse voltage is developed, and what happens? The current, whatever the reverse anode current that was flowing, reverse current, now gradually starts decreasing. Till this T1 to T2, the electrons constantly will be in motion within the layers. Okay. After T2, what happens? The electron slowly comes down till the point T3. Okay. Now, at T3 what happens? At T3 only junction J1 and J3 are blocked. Till then, this J1 and J3 will be in its forward condition, but gradually when this takes place, reverse recovery takes place, only then it goes to the reverse biased condition. So, all this will take place within nanoseconds within a thyristor. Okay. So, what happens? It will slowly turn off, that is J1 and J3 are in the reverse bias state. Next, at J2 what happens? During the time T3 at the junction J2, it is still not in the off state, but there are few charges that are still in motion. Those charges are known as the trapped charges, which will be still responsible for the current to have some value of the current. Okay. T3 to T4, what happens? The carriers recombine. Whatever the carriers which were present within the flow 4 layers are going to be recombined, and this time T3 to T4 is known as the recombination time, gate recombination time. Okay. So, at T4 what happens? Whatever the electrons and holes were there, all have been stopped and settled in their places, and the current goes to 0. Now only the anode current is 0 and completely it is in the off state. Okay. So, this process, this is a general mechanism followed for a thyristor to go to its off state, and these are the process how by step at each instant of time how the changes takes place within the thyristor. Okay. So, this is about the mechanism. Now, depending on whether the source input to the thyristor is an AC or DC, we have different methods of commutation. Now, we will see the different turn off methods, that is the different commutation process. Now, as we discussed previously, whether you are going to give the input as an AC or a DC, depending on that we classify the process of, that is a commutation, into two types. The first type is known as the natural commutation process. Natural commutation means, let us take an example of an AC signal. This is a thyristor. We are going to supply an AC signal. We have a resistor as the load, and this is the supply voltage, this is the thyristor. So, now what happens in this case? We have positive half cycle anode of the thyristor is connected, provided the gate pulses are given to the thyristor. Then what happens? When anode is there and a positive value of the input is applied to it, it goes to the forward biased condition. So, from this point to this point, the thyristor is in the on state, right. Now, reversal of polarity takes place. Reversal of polarity provided with the turn of time. Usually the turn of time will be around the range of 10 to 100 microseconds. This will be the approximate turn of time for a thyristor. Using those values, now at the instant it will not go to 0, but after some duration it will go to 0. Okay, then what happens? Automatically next positive half cycle, again the thyristor is in the on state. Here it is off, here it is on. So what is happening? Without your external effort, automatically on its own it is going to go to its on state, come back to the off state. On, off. This keeps on changing. You are not going to put any effort. So this process is known as the natural commutation process. Without any external circuit, any external aid, it is automatically, because of the input AC, alternating input, it is going to go to its on and off automatically. So off is also a natural process, hence the type of turn off method, that is the type of commutation, is nothing but natural commutation method. Whenever you use an AC as the input source to the thyristor, that process is a natural process. For example, in case of an rectifier circuit, it is a natural process of commutation. In case of a regulator, voltage regulator or a cycloconverter, we have already discussed about it in detail. So, in these two type of applications also, cycloconverters and AC regulators, also this natural commutation process takes place. What is the benefit of this natural commutation? No need of connecting an extra circuit. Circuit is very simple. The complexity is also very less, right? And it can be easily designed. Okay, so this is the process of natural commutation. Now, suppose instead of connecting an AC, we are going to give DC as the input. Let us consider, instead of Vs here, we are going to give a, let us say, positive to negative supply, DC. Now what will happen here? DC, let us say we are connecting a battery of 5 volt. If you are connecting a battery of 5 volt, what will happen in the input signal? Vs, you will always get a constant value of 5 volts in the circuit if you are using. Okay, what happens in this case? Thyristor completely will be in the on state. We don't want that to happen. Why? Because thyristor is only a switch. Switch means what? It should be on and it should be off. It should go on and off required by the circuit designer. Okay, so now what will happen in this case? If it is a 5 volt battery connected to the thyristor, then automatically 5 volts DC, constant steady state voltage, will be applied. Then what happens? Once you give the gate triggering pulse, always thyristor will go to its on state only. Now for this, what you have to do, you want to turn off the device, so forcefully you have to turn it off. Okay, how do you turn off forcefully? By using different elements to this circuit. So here, this type of commutation, whenever your input is a DC, then that type of commutation is known as the forced commutation. You are using a circuit, an external circuit is used, forcefully you are going to turn off the device. Used in the chopper circuit, DC chopper circuit, and in the inverter circuits. You have to use external circuit that is going to help in turning off the thyristor. Okay, so the circuit elements what you are going to use is also, in the case of forced commutation, the circuit elements that you are going to use, and with the help of these circuits you are going to forcefully turn off, that elements are also known as commutating components. Now based on this commutating components, commutative components means usually it will be L or C or a combination of both. So there are different combinations of L and C by which we have different classes of commutation. totally there are 6 classes by which we can commutate by having a different arrangement of the commutating components. We have, it is classified as 6 different types of commutation, out of which you, for your syllabus, we have class A type of commutation and class B type of commutation. This types or this classification is purely based on the commutating components. So what is the aim of this force commutation circuit? 2 important things should be in mind. Anode current should be 0, or in other words also we can say that the latching, the anode current must go below the latching current. Okay. So in that case the thyristor can go off. So using these commutating components, we have to force the thyristor in case of this to go to a 0 condition. Now we will see in detail about class A and class B type of commutation process. So the first type of commutation process is the class A type of commutation process, where we are going to make use of a resonant circuit. Resonant means RLC, if it is in series it is known as a resonant circuit. So here RL is the load resistance. Okay. So the main commutating components what we are using is the L and C. These are the commutating components. Okay. Thyristor is a device which is connected to the DC supply. It's a forced commutation process. As soon as you see the circuit, you will understand that if you are giving a DC supply, it is a forced commutation process which you have to adopt in order to turn off this thyristor. Okay. So now what we have to do? Okay. Initially DC voltage is applied to the thyristor. Once you are applying the DC voltage to the thyristor, what is going to happen? Anode is provided, the gate signal is provided. Anode is connected to positive terminal supply, and hence what will happen here? There will be current flowing in the circuit. Switch is closed, thyristor is a switch. So switch is closed and the current flows through this path. So what happens? You are going to get some output load voltage across the load resistance. So what happens to the L and C? Positive current, positive potential is flowing. So we know that inductor and a capacitor are nothing but energy storing devices, which works with respect to the rate of change of current and with respect to the rate of change of voltage, capacitor. So it is an energy storing device. So now what happens? L and C, L and C. So when the current starts flowing in this circuit, what happens is inductor starts storing energy from plus to minus, capacitor starts storing energy from plus to minus. Okay. Now let us say we are going to apply a 5 volt DC here. So till the value of the inductor is equal to 5 volt, till it is going to store the complete energy, it will keep on storing the energy. By default, thyristor is completely in the on state after we have given the gate signal. Okay, thyristor is in the on state. So on state of the thyristor means it indicates that this is the switch. It is providing a closed path for the flow of current. Okay, now what happens? The value of the inductor till it reaches 5 volt, complete energy is stored, it will start its process or it will be accumulating the energy. Similarly, what about capacitor? Capacitor also on its parallel plates, it will also accumulate charges, let us say till this maximum value, because the input is only 5 volt, till that value you are going to charge the inductor as well as the capacitor. Now anode potential, okay, that is voltage developed at the anode must always be greater than the cathode potential, right? So here if you are having 5 volt here, what should happen? If you are having 5 volts here, anode is there, but the voltage here is still not developed. So this anode potential is higher than that of the cathode potential. After some instant of time, what happens? This potential voltages in series will be added. This 5 volt I am going to use for your ease of understanding. Okay. So 5 volts plus 5 volts, what will happen here? You will be having 10 volt. Okay. 10 volts and 5 volts. What happens? Anode potential is less, cathode potential is more. So what happens? Automatically this thyristor goes to its off state. Okay. So what is happening now? By using an L and C commutating components in series, you are going to turn off the thyristor, you are going to increase. Now what will happen? After it is reached the maximum value, its saturation value, L and C, the property of L and C is the energy will be stored in the inductor, energy will be released from the inductor. Similarly, capacitor, the charges will be stored or charged, the capacitor will get charged. After some instant of time, capacitor will discharge. Okay, this is the law of inductor and capacitor. Now already it has reached 5 volts saturation. Okay, now what will happen? Here already 10 volt. Here what happened to the potential? Anode potential is less, 5 volt is less, 10 volt is more. So cathode potential is increased and anode potential is reduced. So automatically thyristor should go to the off state. Provided along with that, what is going to happen? Whatever the energy was stored, reversal of polarity takes place. When it is 5 volts, reversal of polarity minus plus. So minus plus minus plus. So when at this instant minus plus and minus plus added together minus 10 volt. So at the cathode you are going to supply a minus 10 volt. Okay. So what happens here? The thyristor goes to its off state. Okay. Next, again what will happen? This process will continue. After some instant, now again after this has completely released the stored charges and the capacitor completely discharges, then this will come to 0. It will become 0. Why? Because whatever the energy is stored, completely it is sent out. So what happens? This will again become 0 and so thyristor which was off, now when this potential will become 0, what happens again? This is more, anode potential is more than the cathode potential. So what is happening now? Anode 5 volt turn on. Again after some instant of time, this will be equal to 5 plus 5, 10 volt with a negative sign, negative reversal of polarity. So minus 10 volt is higher whereas 5 volt is lesser. So again it turns off. So this self commutation by its own self, after inserting the commutating components, by its own self it is turning on and turning off with the help of the commutating components L and C. So this is the process of turning off of the thyristor by using a L and C resonant circuit. So it is also known as a resonant commutation. Okay. Now usually if you see here 0 to K, at the point K it will be completely going to its off state. Why we are writing this is because of the L and C, the shape of the waveform is not a straight line but a curved one. Okay. Hope you have understood the working of this class A type of commutation. Now let us start with the derivation in finding out how we can control, by controlling the value of L and C, how we are able to achieve the turn on and turn off times of the thyristor. Okay. So for that we have an expression, let us see it now. Now we have the circuit, let us assume that the thyristor is in its on state, so switch is closed. So there will be a current I that will be flowing in the circuit. So applying KVL to the circuit here, what will be the equation of current? Current V DC is equal to, apply the KVL here, you will get L into di by dt. L into di by dt plus, if you have a capacitor, how will you write the equation? 1 by C integration of I into dt plus you have the resistor RL load plus I into RL. Okay, so this is the generalized KVL that if we are applying it to the class A commutation circuit. Now differentiate the entire equation by d by dt with respect to t. What will you get? D by dt VDC is equal to L into d square I by dt square. So this will continue plus 1 by C. You have an integration term, you are going to apply here differentiate with respect to t. If you are differentiating with respect to t and you have an integration, that will get cancelled and the remaining term will be into I plus di by dt into RL. Okay. Now let us divide the entire equation. Divide the equation by L. We will get, now see here, VDC. Does it vary with respect to time? It is a constant value 5 volts, so no variation. So this value can completely equate it to 0. So we will rewrite this equation. So divide by L the entire equation, you will get it as d square I by dt square plus 1 by C into L I plus RL by L into di by dt. So this is equal to, the voltage is not a variable with respect to t, hence the voltage you can write it as 0. So this represents a second order homogeneous. So we know what is the difference between homogeneous and non-homogeneous. Now the solution, already we have studied in our mathematical modeling, we have studied about the differential equation on second order differential equation and its solution. Using the same solution, we will find out at what duration of time we can vary by varying the value of L and C, how can we find out the off time of the thyristor. This equation represents the second order differential equation and here we have the solution for the second order differential equation. Now for an underdamped case. Underdamped case means the load resistance and the commutating components together, when it is used in a circuit, it forms an underdamped system. Okay. So in detail to explain about the damping, damping is nothing but the oscillations that you are going to come across. Okay. Damping is always represented as zeta. Okay. So depending on this value of zeta, which varies from 0 to 1, we say it as an underdamped case. When it is equal to 1, we say it as a critically damped case, and if it is the value of zeta is greater than 1, it is referred to as a overdamped condition. So the circuit, that is a commutation circuit, which consists of an RL load resistance along with the commutating components, forms an underdamped case. For time being, you remember that if the value of zeta is less than 0, it is an underdamped case. If it is equal to 1, it is a critically damped case. If it is greater than 1, it is a overdamped case. Okay, this in detail you will be studying in your control system chapter. Okay. Now coming back to the equation here, the solution for the second order non-homogeneous differential equation will be equal to e to the power of minus zeta t into a1 is a constant into cos omega t plus a2 sin omega t, generalized equation, where zeta is nothing but r by 2l and omega is nothing but omega naught into square root of 1 minus eta square, where this omega naught is a natural frequency which is given as 1 by root LC. Okay, so to find out the frequency of the underdamped condition, we will be using omega. Here omega refers to the frequency of oscillation, because L and C together comprises of a oscillatory circuit. So keeping that in mind, oscillator means generates its own frequency. So here we are finding out the frequency of oscillation omega. Okay, so omega is equal to, substitute the values, you will get the value. Now by finding out the solution, we will come across A1 is equal to 0 and A2 is equal to VDC by L. Substituting these two expressions in the above equation, we will get solution I of t is equal to e to the power of minus r by 2L t VDC by omega L into sin omega t. Okay, this is the equation, solution for finding out the current. Now, coming back to the waveform which we have already observed for a class A commutation, now we can see that at omega t is equal to pi, what happens to the current? Current is equal to 0. Now substituting the value here in the above equation, we will get the solution for omega t is equal to pi by root of 1 by LC minus r square by 4L square. Now when we substitute this for omega t is equal to 0, that is if it is greater than 0, then it is a underdamped case. So we are going to take the omega is the frequency, okay, whereas zeta is the damping oscillation, okay. So for the underdamped case, the omega should be greater than 0, the frequency must be higher than 0. So then only the system will go to its underdamped case. So 1 by LC minus r square by 4L square is greater than 0. Substitute the equation, that is bring this minus r square by 4L to the other side, you will get 1 by LC greater than r square by 4L square. So when you are going to equate it, what will happen? You should find out what is the value of the load resistance that you can use for the given values of L and C. Depending on this condition, the value of the load resistance should be less than this 4L by C, L and C are the commutating components. If this condition is satisfied, while designing the class A circuit, care must be taken that the value of L and C, what you are going to choose, which should be, the value should be less than the resistance, load resistance. So in this case, if you are using the element, then we can attain the resonant commutation. So this was for a series resonant circuit. Previously we saw the class A type of commutation for the load that will be connected in series, that is the commutating elements will be connected in series with the load. Now in the same case, class A commutation itself, if we are going to connect the load resistance in parallel to the commutating circuit, commutating component, then what will happen? Okay, almost a similar process. So here what will happen? With the application of some gate signal, you will turn on the thyristor and capacitor will gradually charge. So when the capacitor charges, when you are going to get output voltage, we know that in case of a parallel circuit, the voltage, that is the output voltage what you are going to get is, if it is a parallel circuit, it will be the same output voltage. So whatever the voltage you are getting across the capacitor will also be equal to the output voltage what you are going to get, since it is a parallel combination. Okay. Now with the application of gate signal, what happens? The SCR goes to its on state with some delay. Okay. And when it is again off, so see here with respect to the voltage, when the SCR is in the off state, there will be a voltage. So when the SCR or the thyristor is in its on state voltage drop is 0.7. So we represent this as the on state. Okay, so on state is nothing but a straight line. So this straight line, what happens? It will not stop here. Why? Because of the minority charge carriers, as we have previously explained. By making use of this L and C, that is again the charging will take place. The charges will get accumulated on the plates of the capacitor and energy will be stored in the inductor. Reversal of polarity takes place. Cathode potential is more when compared to anode potential, automatically the thyristor goes off. Using that process of commutation, we are going to turn it off. Okay, so this duration of time is known as a turn off period. Then again there will be a high voltage available at the SCR, whereas there will not be any current flowing into the thyristor. So this is the basic operation for the class A commutation itself, but when the load is in parallel with the capacitor. In the next session, we will be discussing about the class B type of commutation. Thank you.